Okay. Good evening, everyone. Welcome to week 3 of Probability for Computer Science and PTL course. My name is Bhavya. I'm a PhD scholar at IITM in the Computer Science department. Okay. So let's directly switch to this type's content. So far, we've seen the basics of probability. This was in week 1, and in week 2, we saw conditional probability. And this was in to do with independence and Bayes theorem and so on. This week's content is about random variables and expectation. Okay, so I hope you guys watch the lectures. Okay, and so I won't be covering the theoretical component. Rather, I'll just be solving problems. So we'll be solving lots of problems based on random variables and expectations, so that you are familiar with the content, and so you can easily take a problem based on probability and expectation and easily get into solving mode. Okay, so just to be quickly clear that what is a random variable? It's called a variable because it can store several values, but rather it's more of a function. Okay, which takes an event and then maps it to a real number. So theoretically, that's what it is. But of course, I can always allocate whatever. I can define the function however as I want. For example, let's say the random variable says one if uh, a die that is thrown, okay, is even, and zero otherwise. Okay, and so it can be something like this. And what is expectation? Okay, what is expectation? Expectation is the um, as the name suggests, it's the value that you expect. Okay, for this random variable to happen. So the idea is that the random variable follows a certain distribution. For example, here it's either 1 or 0. It need not be that. For example, I can define another random variable y, which is like 1, 3, 7. Okay, 1, 3, uh, 5, 7. It can take these values, let's say. Okay, and or let me write 1, 2, 3, 4, and so on. One whenever die uh, die output is 1, when it is 2, 3, and so on. This could also be another the random variable. You can assign it anything, but the key point is what should you so what do you expect the outcome should be? Okay, that is a good measure, is what is called expectation. Okay, and expectation is nothing but the sum over all the possible, okay, events, and then you have probability that x is that w, and multiplied by the random variable itself, x. Okay, for example, when this was the case, you have expectation of x, okay, equals, well, the die throws could be even, or the die throws could be odd. Okay, sorry, x could be 1 or x could be 0. So or w is actually in the range of x. Okay, so here either x would be 1 or 0, and expectation of x is the sum over probability that x equals 1 times x plus probability that x equals 0 times 0. And what is the probability that x equals 1? The die throw is even, so which is either 2 or 4 or 6. So three possibilities times x plus 3 by 6 times 0, which will give you 3 by 6, which is nothing but half. Okay. So the expectation is an abstract value. Notice that half is not like a number of throws. Okay. Half represents that, okay, something like half of the possibilities, okay, will be even. So it's an abstract concept, okay. But the key thing to note is that we always say that expectation is something like average, right? Expectation is average if all the possibilities are equally possible. For example, like if we say, um, uh, okay, but we'll get to it. We'll get to it. I just wanted to give you a quick recap of about expectation. Okay, and recall that this is called a Bernoulli variable. Okay, and because these two outcomes are exactly separate, and furthermore, okay, furthermore, um, this guy is also called indicator random. Okay, because it indicates an event, one or zero. Okay, so that was a quick recap. Now we'll just get into solving problems. Okay.
So what about the journey from the real number to the sample space? Like in this function, say I got the average value as half.
Hmm.
So which outcome of the random experiment corresponds to the numerical value half?
Okay. So that's the thing. So this is an abstract concept. Okay, expectation is an abstract concept. So the better way to visualize it is the following. Okay, you map it as a graph. Okay, and so one, so it's a die throw, right? Two, three, four, five, six. Okay. Now what you do is, okay, yeah, Kishore, I'll come to it. Okay, I'll come back to you. So now what you'll do is you'll look at the probability, okay, or the frequency of them happening. Okay, so the probability. So this is the outcomes. Okay, let me call it A, and probability of A is for a fair die. It is 1/6, right? Let's say this is 1/6. So this is the probability. Okay, you can interpret this as frequency also. For example, if you throw 100 times, then 100/6 is what, something like 16.6, right? So with so then you'll get some plots like this. Okay, it will follow this line. Okay, it will be a straight line. Okay, just one moment.
Yes.
Right now, what you are saying is, let's say you say, what is the probability? Okay, that let me change my random variable a bit. What is the random variable? X equals 1, 2, 3, 4, 5, 6, such that outcome is 1, outcome is 2, and so on, and outcome is 6. Okay, and we all know that probability of x equals any I, okay, in this case is 1/6 because it's a fair sided die. Then what do you have? Expectation of x, okay, for this x is 1/6 times the first probability p of x equals 1 plus 1/6 times the first probability x equals 2, and go on till 1/6 probability of x equals 6. Now what do you notice? um
No, sir, there is wrong. You written the formula. So 1 into probability of x equals to 1 plus 2 into
yeah,
probability of
yeah,
x
okay,
equals
okay,
to.
sorry, yeah, thank you. Each of these probabilities are 1/6. Yes, sorry. 1 into probability that x equals 1 plus 2 into probability and so on till 6, right? So these are the values of x's, right? Now, what do you have? You have 1 times 1/6 plus 2 times 1/6 plus and so on 6 times 1/6. And 1/6 you can take it outside. It is 1 plus 2 plus and so on till 6. But what is this? This is whatever it computes, 1 plus 2 plus and so on. Okay, it should be computing 3.5, I think, right?
3.5.
Right. So it should be computing 3.5. What is 3.5 here? 3.5 is here, the middle. Where is the color? 3.5 is here, the middle. So what it means is it computes the average for this uniform distribution. But does it mean when you throw a die, you will get you expect 3.5 to show up? That's not what it means. But the idea is more abstract. So the idea is more abstract that it is the probability mass is distributed, okay, from 1 to 6. So it is distributed in such a fashion that where the average of these outcomes, because of these the mass are uniformly distributed, it'll lie somewhere here. And the distribution, if it is something like this, then because of the average, it'll be something like here. Okay. But Goel, the question that you asked, as a real number, okay, how do you interpret it? Okay, it as a real number, you can interpret it like what is the closest range in which it will occur. Something like 3 and 4. Okay, this is something. So you can expect 3 and 4 to be a range in which these variables occur. But since it's uniform distribution, 3.5 does not tell anything to us. Okay, 3.5 basically says that since I'm stretching from 1 to 6, 3.5 is the middle and it can lie anywhere in between here. You need better parameters. You need like covariance and variance and things to say better things about the distribution, because 1 and 6 are equally spreading it apart. But if it so happened your expectation is moving more to the right, then you know that there is a certain bias in the system. Okay, it is moving more to the right. Then you have a certain bias to the system because the probability mass function is actually stretching the expectation to one side. So the distribution is becoming more skewed. So that you would expect in a distribution which looks somewhat like this.
Yes, but then my quick query was also related to the existence of an inverse function.
Yes.
Do we have such an inverse function that, and not related to the expected value as such, but then the inverse function, as in the definition of the random variable?
Yes.
So like say if I take the inverse of the real value, then would I be able to get the event corresponding to, event in the sample space?
Yes, that is a good point. Now, see, if your random variables should be a surjection, okay, in some sense, okay. So if because you can invert a function is invertible only if there is a unique value that you start with, right? So for example, you know that so if you say x of the event that x is equal to the event that if die is thrown is even, okay, sorry, which way is it? Yeah, if die is thrown is even, then the value of x is 1. So can you say that if x is 1, then the die thrown is even? Yes, you can, because there is a unique mapping. Die thrown is even, then you have x. Okay, so even, odd, 1, 0. This function is invertible, and that is by
Okay.
definition of a random variable.
All right, and because I cannot have any other value except 1 and 0.
Because you can't have any other value, but you can increase the values also. For example, like this, and this is still fine, right? This is invertible. So
All right.
yeah, right.
Yes, fine.
Yeah, Kishore, you're saying something.
Yeah, Bobby, we may continue.
Yeah. Oh, okay. Yeah, Harsh. Okay, one.
I got my answer
Oh,
in the discussion.
Okay. Additionally, Goel, yeah, Yeah, Harsh, okay, you've written in the chat. I joined a little late. Could you tell what will be covered today? Oh, okay, okay. Yeah, Harsh. So what will be covered today is this week's content, which is random variables and expectation. Okay. This is all that will be covered in detail. Okay. And Goel, the invertibility that you talked about, right?
Yes, yes, yes.
So there mm, could be a you this, but this is true only for particular kind of random variables, the invertibility. Okay. You could um, no, a random variable could not be in too many states. No. That's all right. Forget what I said.
Yeah,
Yeah,
fine, fine,
yeah.
fine. Yeah.
Okay,
Yes, yeah.
good. Okay, so now that we have that clarified, okay, so here's the question. Okay, monkey types on a 26 letter keyboard that has lowercase letters only. Okay, each letter is chosen independently and uniformly at random from the alphabet. If the monkey types 1 million letters, what is the expected number of times that the sequence proof appears? Immediately, you see that there is a question about expectation. Okay, what is the expected number of times the sequence proof appears? So you have a 26 letter keyboard, okay, A, B, C, and so on till Z, and there's a monkey which is typing on it. Okay, now the monkey is choosing the letters uniformly at random, independently and uniformly at random. Okay, what does independently mean? Independently means like if he had written an A, it will not affect the next letter that he writes. And what does uniformly mean? Uniformly means the probability of writing A is equal to the probability of writing B is equal to the probability of writing C, and so on till all the letters. Okay. So if the monkey types 1 million letters, what is the expected number of times the sequence proof appears? So let me ask you, what could be the final random variable that you want to? So you are supposed to compute an expectation, right? Expectation of x. So what should x be? What should x be? This random variable. So as the question says, it's expected number of times sequence proof appears. Okay. Oh, but in case you are confused, okay, I'll just repeat the question once again. Okay. So the monkey is okay. The monkey is typing like 1 million letters A, B, D, C, Z, Z. It could repeat X, W, B, 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 X, and so on. And this is, he's doing it randomly, and he's doing 1 million letters. Okay. And the monkey does not know what these letters are, right? But accidentally, I mean, by chance, okay, he is it may so happen that he has chosen a P and he has chosen an R after that and chosen an O after that and chosen an O after that and F after that. It just so happens that he did this. Maybe he did it in this location, and maybe he did it in some other location. Okay, and he wrote proof. Okay, how many these proof? How much? How many proofs do you expect? Sorry, how much? How many times do you expect this sequence of word proof to appear when you type it? That is what the question means. Okay, I hope that's clear. Yeah, go ahead.
So initially I was initially I was thinking that if the monkey types P,
Uh,
then I will consider this as 1, and otherwise the value is 0 for this random variable x.
uh,
But since here the order also matters, like after P I should get R only.
yes, yes,
So now I think that if the monkey types proof PROF,
yes.
then I will consider the value of the random variable as 1, and otherwise the value of the random variable would be 0.
Okay, good. That is a good approach. Okay. Yeah, Kishore, go on.
Uh, See, as we said,
Yeah.
it's 26 letters, right? So 26
Right.
letters out of 26 letters, the expectation of only 5 letters we are expecting.
Yes.
So it's a summation of summation of each letter of their probability.
Summation of each letter and their probability.
Summation of the probabilities of each letter. I mean to say. I
Summation
mean to
of
say,
probability of each letter.
yeah. I mean to say P 1/26, R 1/26, O
Ah,
1/26.
okay, got it.
Again, O is also 1/26 because it is replaceable event,
Okay, okay,
and
okay,
F again 1/26.
okay, good. Okay. And so P
Of course,
the
there is another hook there. It says the question says 1 lakh times it types. So
yes,
probably I'm not able to. I'm not understanding how to correlate that with this answer.
okay,
I'm a
okay,
bit
okay,
confused.
okay. But you are almost there. Good. So what Kishore is saying that is at any point of time the probability that you write proof is, you since it's uniformly distributed, it's 1 by 26 times 1 by 26 times 1 by 26 times 26. That's how you choose PROOF at any point of time. Yes, someone had raised their hand. Was it Harsh?
Yeah, no, I actually
Oh, yeah,
wanted to
Harsh.
ask
Huh.
that can the linearity of expectation be used here, like expectation of x plus y, that formula it splits?
Yes. We will be using linearity of expectation. That's right.
Okay, like expectation of x is like p, expectation of p, and then r, and then o, f, and then we split the whole thing.
Oh,
Is
okay. That
that is wrong,
up till
right?
that level, it's not required. You can do it in a more high level, okay. But linearity of expectation will be used here.
But I didn't understand the whole this whole question. Like, how can we even approach this? Like, proof? Like, is this like we have to formulate different types of wide letter words, or we have to just pick up the alphabet probability, or you have to
Ah,
find what we
okay.
have to do? Like, I don't know where to target it. The
I'll do
alphabet
it
or
step
the
by
word.
step. Don't worry. Okay,
Yes.
I'll
Can you
do it
just
step.
tell the idea?
Yeah, okay. It's don't worry. I'll do it step by step. Furthermore, the main crux in this is choosing what the random variable should be. Okay, and this entire section that I'll do 4 to 5 questions will be based on indicator random variables. Okay, now here's how you use them. Okay, so we have collected ideas from you guys. Okay, yeah, Shubhan.
Sir, can we break? Sir, can you show the question, please?
Yes.
Sir, if you break this question in like that, first the monkey is typing only 5 letter, okay,
Okay.
and what will be the expectation to get
Huh.
this sequence proof?
Yeah.
Okay,
Huh. Okay.
then we will get some expectation for these first 5 letter,
Yes.
and we can continue this sequence up to 10 lakh letters
Huh. Okay.
by multiplying it into 10 lakh by 5.
Multiplying it into 10 lakh by 5. Okay. Oh, okay. Yes, that sounds like a reasonable strategy. What Shovan is saying is, at least what I understood is, he wants to divide into 5 letters each, right? Shovan,
Yes, sir.
groups of 5 letters each, and say what is the probability that this is proof, what is the probability that this is proof, and so on. Is that what you mean, Shovan?
Yes, sir.
Is that what you mean? Like divide it into blocks of 5. That's why you said 1 million by 5, right?
Almost like that. I just can't
Yes.
clearly say that what I'm just thinking.
Okay.
But
Just a
it's
small.
almost like this. Yes.
Yes. A
Let's
small.
just break it into chunks and then calculate the overall probability.
Yes. But an issue is that proof can start from here and end here also. Okay, you group them into blocks of 5, but the proof can be overlapping between the two blocks. The one word proof may, PROF may overlap between two blocks. So you need to
Yeah,
consider those
that's
possibilities also, right?
yeah.
Yeah. Okay. Yeah, just a moment, Harsh. I think Kishore raised once first. Yeah, Kishore.
Yeah, see, of course, but this event has not happened. It's the expectation is before happening, we are predicting, right? So we can't break them into five-lettered word and then we predict it.
Yeah, but we can look at all possible outcomes and then try to guess, right?
So the extension of my answer to the earlier is, see, of course, we got the summation of probability of each letter
Yeah.
that should be divided with 10 lakh letters. So probably that gives some random variable x value.
Yes. Yeah. Yeah. Kishore, I'll add to your idea soon. Okay.
Okay, fine.
Okay. Good. So yeah, Harsh. Okay.
What I think is that we can assume proof to be one alphabet, one string, and then
Okay.
we can utilize that. We can say 10 lakh minus 5, which is the number of letters that have been entered.
Okay.
And then we can just add 1 to that, because proof is just one letter. We're just assuming that proof as a word is just one letter. So, and then we can consider.
That is yeah. Harsh, that is somewhat similar to what Shovan was also saying.
I didn't
Okay.
listen.
But Shovan is saying, like, look at it into blocks of um, uh, 5.
No, not blocks. I'm saying that we can assume that everything else other than proof is letters, and proof itself is also a letter, like that.
Proof is also a letter, right?
Yeah.
Okay, I get it. And proof is a letter that takes like weight 5, right?
Hmm.
So a slight complication that might have, but it's a good strategy. Okay, you are abstracting it out. It's a good strategy. A slight complication that may happen is,
Hmm.
let's say, for example, this letter P hat represents proof.
Hmm.
Okay, this P hat represents proof. For example, if monkey writes P hat here, it means he has written a proof here.
Yeah.
And let's say he has written P hat here, it means he has
Mhm.
written proof here.
Mhm.
Okay, that's what you mean, right, Harsh?
Yes. Exactly.
So now the issue with that is, I mean, it's not an issue really, but you need to be careful about this. Is whenever he writes P, he has used up a budget of 5 letters.
Okay, but I didn't understand that.
Okay, he has a budget of writing 1 million letters, right? That's his budget.
Mhm.
As soon as he
Okay, I
writes
get
P
it. I
hat,
get it.
yeah,
I
you
get
get
it.
it, no? He
Yes.
has removed a budget of 5 letters.
I get it. Yes.
And so the length is sort of changing now,
Mhm.
depending
Yeah.
on like whether the number of P hats will determine like the length of the string you string you
Yeah.
have. That is one thing you need to be careful about. The other thing you
Mhm.
need to be careful about is each of these letters occur with probability 1 by 26, because they are
Mhm.
uniformly chosen across the alphabets.
Yes.
But what is the probability of choosing this letter? Is it 1 by
That is
26?
another question. Yes.
So see, the letter A occurs with probability 1 by 26. B
Hmm.
also occurs with probability 1 by 26, because they are uniformly and randomly chosen from the set of English lowercase letters, right?
Mhm.
But this letter P hat,
Mhm.
does it occur with probability 1 by 26?
No,
No.
that would not be the
You need to
case.
choose P and then R, then O, then O, then O, then
Mhm.
it's 1 by 2 to the power 5, 26 to the power,
Mhm.
right? So this is another thing you need to take care about,
Yes, got it.
right? So the process could become more complicated, but I would encourage you to explore it. Okay.
Or we can
But
just do that for convention, just for easier solving.
yeah. Okay. Sure. Okay. So now I will uh, now I'll explain the solution to you. Okay. Now please look carefully, and then we'll take questions. Okay, if you have any. So, like I said, what is expectation that finally you need to take? Okay, what is the expectation that you finally need to take? So let me remove this in case you guys get confused. Okay. What is the expectation that you guys need to take? Expectation of x is the number of times. Okay, x should be the number of times proof appears. Okay, number of times proof appears. this is straightforward because that is what the question asks. So which means that x, the random variable x, is the number of times proof appears. Simple as that. Now we'll use two very powerful ideas. Okay, the first very powerful idea is the strength of indicator random variables. Okay, and second is the principle of linearity of expectations. Okay, what does linearity of expectation say? Expectation, okay, says expectation of x plus y is equal to expectation of x plus expectation of y. And the best thing about this, okay, this looks simple, but it's very powerful. Why? Because x and y need not be independent. They could be even dependent events, dependent random variables. This will always work. Okay. Now, so this is expectation plus expectation of y, and they need not be independent. Okay. Now, good. We'll come to solving the question now. Let xi be defined as the word proof appears at position I. Okay, I hope you are starting to get it. Xi represents the event that, oh, okay, sorry, it's not a, it's a random variable. Sorry. Represents, so it should be indicator random variable. So it outputs a 1 if proof appears at position I. Okay, and 0 otherwise. Okay, proof appears at position I and 0 otherwise. Now observe this. Observe that x, the random variable x, is nothing but summation xi from I equals 0 to, for now this is incorrect, but I'll say it. Okay, for now. Okay, actually it's not incorrect also. Okay, notice why this is true. What is x? Number of times proof appears. And what is xi? Xi equals 1 if proof appears at position I. So x is nothing but some summation of xi's, no? So because, for example, okay, if you are confused, I'll give an example. Example: proof, the letter proof, the word proof appears at positions 1, 8, 100, and that's it. Okay, that means x1 outputs 1, x8 is 1, x100 is 1, and every other xi is 0. Okay, so number of x is summation xi, which is uh, x1 plus x8 plus x100 plus 0 plus 0 plus 0. These are what are contributed by the others, and this is nothing but 1. These are indicator random variables. Okay, so they can only have values 1 and 0. That's how we define them, right? 1 plus 1 plus 1, because only those events will contribute a 1, okay, where proof has appeared. Okay, only those random variables will, xi's will contribute a 1 to this sum if it appears at position I, so which is equal to 3, which is true. There are only 3 positions where proof appeared. Okay, so is this clear? This is very important. We are going to use it everywhere from now. Is this clear? So a little off topic, but are the lectures recorded? Yeah, yeah, it is. It is recorded. Okay, okay, it's clear as to show one. Where are they available? Actually, they should be giving you a sheet where the lectures are. It's there in my channel. Okay, YouTube channel. I'll just share you the channel. But others, I hope it is clear.
I mean, why to store the value of I? Wouldn't be sufficient to say that okay, this is the expected value of getting proof in one iteration, and then I can multiply that expected value by the value of 10 million, whatever the given value here is,
Yeah.
and that would be the overall expected value. I mean, where is the need to store this I to keep this information?
No, but how do you? Yeah, go on. How do you? Sorry. I can you repeat once again?
So my point here is that
Huh?
what is the expected value of
Huh?
getting this proof?
Huh?
Once. In one experiment, monkey is typing how many times?
1 million times.
1 million times. Okay, so what is the probability of having this proof? 1 by 26 raised to the power 5.
Yeah, that's right.
And I compute the expected value of this simply by taking this indicator random variable, and the value came out to be what? 1 multiplied by 1 by 26 raised to the power 5. Just one summation, and plus 0 multiplied by something, but then it's fine. So and then I multiply this entire result by 1 million times,
Huh?
because assuming that I cannot repeat it. So I was under the impression that this entire experiment is equal to x repeated 1 million times. That is not right. That is not right.
Yeah,
I think.
yeah, I'm not sure. But okay, I'll complete this argument. Wait. Then we'll take it. Okay.
Sure.
Okay. Yeah, Kishore.
See, as per the explanation,
Yeah.
see, we have to check whether the sequentially PROOF is repeated.
Huh.
Then that should be counted as 1,
Huh.
right? If it is typed sequentially PROOF,
Yes.
those hits should be counted as 1 time. So if that repeats, those many number of times should be summed up, right?
Yes.
So then, but see, once it types P,
Huh.
and then there should be it hits again another letter, which should be expected as the R letter,
That's right.
right?
We'll come to that. Yes.
So then, how can we calculate the probability of after hitting P exactly there would be a R, because if it is already done that, then based on that we will calculate. But the event has not happened, but we are trying to calculate the expectation, right?
Yes.
So then apart from this counting, summing up the ones, we should also take into consideration the probability of hitting R before after P, and then OO before R.
Yes.
That's the problem.
We'll
How
do
will
that.
we?
We'll do
Okay.
that also. Okay. But I or in case, yeah, Ankita.
Can you explain how x equals to 3 is calculated?
So So what I'm trying to do, Ankita, is justify this. Okay, my value x represents number of times the word proof appears. Okay, Ankita, I hope this context is clear, no, about typing on the keyboard, right?
Yes, sir.
Yes. Okay. Okay. So my x represents number of times proof the word proof appears when the monkey is typing. Okay, is equal to sum of the indicator random variables xi, where each xi represents xi is 1 if proof appears at position I. Okay, position 1 2 3 till 1 million. Okay, at position I, if the word proof appears, then I'll put the indicator random variable as 1, and if xi is 0, sorry, if it does not occur at position I, then it'll just output 0. Okay, now for example, let's say the word proof appears at position 1 8 and 100. Okay, so you can imagine something like PROOF, and this position is 1 2 3 4 5, and 6 7 position is something like AB, and then 8th position is again PROOF, and 9 10 11 12, and so on till 100, then you see PROF again. This is the sequence. Okay, if this was the case, then the random variable x1 would have output a 1 because proof appears at position 1, and x8 similarly would output 1, and x100 should output 1 because, okay, this should be 100. At position 100, proof appears. Every other xi, for example x2, should output 0. Why? Because x2 writes ROOFA at x2, sorry, at position 2, ROOFA, which is not proof, so it will output 0. So every xi outputs a 0 if there is a proof is not occurring at that position. PROF is not occurring at that position. So now let's compute this summation across all xi's. Okay, so this is x1 plus x2 plus x3 till x1 million. But note that, see, x1, x8, x100 are the only ones that contribute a 1 in this case. Every other value contributes a 0. Right? Every other value contributes a 0. That's what we saw just now. And then what do you have? Well, there are only three places, 1 800 where it happens, and each of these xi's, x1 x8 800, contribute exactly 1 1 to the sum. So there are three such positions. So what do you have? You get 1 plus 1 plus 1 is equal to 3, which is what x should be representing, which is the number of times proof appears in this string. Is that clear, Ankita?
But here we have just considered that it appears at the position 1, 8, and 100. But there could be a possibility that it will appear even more than that.
Yes, it could be. I'm just giving an example. That's why it's not a proof. Okay, this is an example. It could be more, but notice that if it was like 1 800 and 1001, then what will happen? X8, x1, x8, x100, and x1001 will all give 1 1 1 1 to the sum, and therefore it means when you sum them up, you'll get 4. Right, which is the number of times proof appears.
Okay.
You get it, no?
Yes.
Okay. Now I'll just slightly correct this summation. This should not be n, but it should be n minus 4, because the last 4 positions, it does not make sense for proof to appear there, because proof is a 5-letter word. Okay. Now we come to the main part. Okay. Now how do you compute expectation? Now it becomes very straightforward. Let me show you. Expectation of x, that is what you want to compute, is equal to expectation of we use this. Okay, let me call this 1. Okay, so expectation of x size I equals 1 to n minus 4 times oh, no need to do times right now. That's all. Right, now recall the linearity of expectation. x plus y, we can distribute the expectations across the random variables. So by linearity of expectations, you get expectation of xi, x1 plus expectation of x2 plus expectation of x3 plus and so on expectation of xn minus 4, right? By linearity of expectations, you have this. Now what about this? We'll use the formula of expectation now. Expectation of x1, okay, um, why did you write n minus 4? Why? Because Harsh, let's say so let's say, wait, do I have space somewhere? Okay, I have this corner here, right? Let's say this is my word 1 2 3 4 and so on till here, which is n, right? So I cannot because n, which is 1 million for me, I cannot write proof here because it's exceeding my length. And similarly, I cannot write proof here, it's still exceeding. Okay, and I cannot write proof here also because it's still exceed. I cannot write proof here also. Okay, so let me make it longer. Okay, and I need to write proof here, PROO. Okay, let me shift this here, PROOF. So this is n minus 1, n minus 2, n minus 3, n minus 4. So n minus 4 is the last place where proof can, where the term, where the word proof can exist. Okay, so that's why n minus 4. Okay, so expectation of x1. What is the formula for expectation of x1? Okay, now we do expectation of x1 equals 1 times probability that x1 equals 1 plus expectation of x1 equals 0 times probability of x1 equals 0. Okay, and so on for the others. For x2 also same thing, equals 1, probability of x2 equals 1 plus and so on. Okay, clear thing to note is, okay, that um, wait one moment. Oh, why am I writing x? Okay, it's the formula of is 1 times this times 0, 0 times this. No, this is the formula of expectation, right? The different values, okay, times so on. Okay, let me rewrite this so that you don't get confused. Okay, x1 can take values 0 and 1. What is the formula of e of x? It is whatever first value it can take times probability of that random variable taking that value, plus what is the next value it can take times probability that what is the uh, probability that it takes that value, plus 1 times probability that x2 takes 1 plus 0 times probability that x2 takes 0 and so on. But what do you have? This is equal to 0, this is also equal to 0, right? So what do you understand? This is another important takeaway of indicator random variables, okay, is that expectation of x equals probability of x for any indicator random variable. Okay, let me call it I so that you don't get confused. Okay, any random variable I. Okay, this also will be using in the following problems. Okay, this is another advantage of using indicator random variables. Okay, so it's just p. pi. Okay. So, but now what do you have? What is the probability that proof is written on? Okay, so what does this become? This is equal to PR x1 equals 1 plus PR x2 equals 1 plus PR x2 equals 3 equals 1 plus and so on till PR x n minus 4 equals 1. Okay. But I think Kishore was mentioning that what is the probability that what does x1 equals 1 represent? It represents what is the probability that proof is in the first position. X2 equals 1 represents what is the probability that proof is in the second position, and so on, right? And since these events are independent and uniform, the probability is same for them, which is 1 by 26 to the power 5. Because the probability that I choose a P is 1 by 26, then the probability that I choose an R is 1 by 26, times probability that I choose an O is 1 by 26, times 1 by 26, and so on, 1 by 26 power 5. Okay. And okay, is that clear? Plus 1 by 26 power 5 plus, yeah, go on, Kishore.
Yeah. Okay. I was about to ask, is it 1 by 26 the power of 5 is for each letter, right?
Not 1 by 26 is for each letter. 1 by 26 power 5 is specifically for PROOF. What is the probability you'll choose a P followed by an R followed by an O followed by an O followed by an F? Since
Okay.
since this is independent and uniform, yeah.
So within the sample space, 1 million letters, we are directly taking the probability of each word. That is 1 by 26 to the power of 5. Is that right understanding?
The sample space is the 26 letters. Okay.
Okay.
Okay. The sample space is 26 letters. And what is the probability that I write PROOF at any point of time? Since these are independent and uniform. Uniform means 1 by 20. I mean, each of these letters are picked with equal probability, which means 1 by 26 probability, right? So
No, but we have 1 million, 1 million words, right?
yeah, 1 million words. We no, 1 million is the length of the letters, but that is
Letter.
separate. We are not sort of choosing letters from the 1 million string. The monkey is choosing uniformly one of the 26
Okay.
letters in the alphabet and then typing that.
Okay, we are taking event as hit. It hits, not the word.
Yes, yes. He's choosing from the set of letters. No.
Okay.
Right? Okay. And
But
what is
see
going
here again, we are summing up the same figure multiple times. 1 by 26 to the power of 5 and plus 1 by 20.
Yes, yes.
Uh,
Can you
this
tell
is
me?
confusing.
Yeah. um, yes, but see, break it down into parts. What is the probability that px1 equals 1, which is what is the probability that I write PROOF in the first position? What the important thing is, the position does not matter because these events are uniform and independent. So at any point of time, the probability that you write proof is 1 by 26 times 1 by 26 times 1 by 26, 5 times. Okay. Coil says whatever is the final value, it would be same for any 5 word, not specific to proof. Exactly. If you change it to another 5-letter word, let's say apple, the probability it's not specific to proof because there is no the function, the distribution is uniform. Well, it treats all the letters equally.
So it just simply to understand, first 1 by 26 is the expectation from the 26 letters, and then to the power of 5 is from the 5 letters.
Yes, probability. Yes, that's right. Okay, good. So 1 by 26. So how many times? N minus 4 many times, right? So in other words, How many times do you sum it up? I equals 1 to n minus 4. What are you doing? 1 by 26 power 5, right? So which is nothing but you are summing up 1 by 26 power 5 n by n minus 4 many times, which is nothing but n minus 4 times 1 by 26 power 5. This is clear, right? You are summing 1 by 26 power 5 n minus 4 many times. So it's nothing but n minus 4 times 1 by 26 power 5. Okay. But what is n for us? N is 1 million, no? N is 1 million. So this is what expectation of x. Expectation of x equals 1 million minus 4 times 1 by 26 power 5. So can someone calculate this probability? Yes, calculate this. This is 99996 times 1 by 26 power 5. Can someone calculate this? Okay, there's no calculator here. Okay, Shovan is saying, oh, why is there a 0.0? Shovan, I'm not understanding. Okay, what is 26 power 5? I feel like 26 power 5 should still be smaller, no? Oh yeah, 26 power 5 is actually a big number. 11881376. Okay, Ankita, okay, both of you are saying 0.084. Okay, so this is coming like 0.084. Okay, no problem. Okay, now let me slightly change the question. Okay, what if n was like 10 power, okay, it was, so how many letters do you have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So which is 1 billion. What if this was the case? Then what is E of x? 10 power 9 minus 4, 1 by 26 power 5. Okay, can you recalculate now? If n was 1 billion.
Seems it is 0.0841.
Yes, but now I've changed it. 10 to the power 9 instead of 10 to the power 6.
Okay.
Something like 800 or something like that, I think. 84. Okay. Yes. Okay, great.
84.16.
84, right? 84.16. Okay. So this is a surprising fact. No. Okay, although I mean the monkey is typing like 1 billion times, okay. But the surprising fact is there is a very, very good chance that proof will appear. And in fact, the expected number of times that you expect this word proof to appear is 84 times in that sequence. Okay. 84 times in that sequence. Okay. Now if n is tending, yeah, one moment, Kishore, closer and closer to infinity, then expectation of x will also be closer and closer to infinity. Okay. Yeah, Kishore.
See this linearity of this expectation, the concept you have just used it here, right?
Yeah.
So this always applies to the sequence of any events. Only applies only when we are trying to calculate the expectation of sequence of events.
No, 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 no. That's the beauty of linearity of expectation. It's so powerful that you don't need the events to be independent or dependent. I mean, it could be dependent even, Kishore. Okay, and it need not be sequential. You can think of expectation of x plus y, where x represents like the I don't know, number of balls picked, and y represents the number of balls which are red, which may be happening together, right? It need not be sequential. Okay, linearity of expectations need not be sequential. That's the beauty of it. Okay, Kishore.
So basically, when we are trying to calculate the linearity, right, in literal format, what we are trying to, get to know.
What are we trying
I
to
mean,
get to know?
yeah, when we say the linearity of this probability, when we are trying to know, is it something we are trying to know the event after event which we are expecting?
So linearity of expectation is rather a tool, okay, to say that okay, I need to calculate the expectation of this random variable, okay. So I need to calculate the expected number of outcome A or something like that. Then
Yeah,
I
that
say
is the
that
that is the basic part, right? So expectation is different, and then linearity of expectation is different, right?
no, no, no.
Both are different.
Linearity of expectation is about breaking up expectation into different parts. See, linearity of expectation says expectation of x plus y is expectation plus expectation x plus expectation.
So if when you say just expectation of x, that means it's only one event, right? No, not on one
No,
event, only
it's
uh,
a random variable.
random variable. Sorry, sorry.
So
Yeah,
yeah.
so when we are trying to calculate
Huh.
expectation of more than one random variable, then the concept of linearity of expectation comes into picture. Am I right?
Uh, uh, um, so see x is see, for example, x here, okay, is a random variable, so it need not represent just one event. Okay, it could represent a
No,
multitude of
yeah,
events.
yeah. I misspelled it. Of course, x
Sorry.
and y are both are random variables.
Yes.
So when I wanted to just calculate the expectation of one random variable, that is x,
Huh.
so that time the linearity of expectation comes into picture, or it doesn't.
Oh, after that, if you can break up x into further random variables, sure. If you can break up x into some, alpha 1 plus alpha 2 and so on, then if you can break up x, then you can use it once again, sure. But if you are not able to break up, then you can't use linearity of expectation. It's to break up random variables that can be described as a sum of random variables, which was true in this case. For example, x equals summation xi, right? So x can be represented as a sum of xi's, and therefore we said this expectation can be distributed into each of these xi's. Okay, is that clear? This is the scenario in which where you can use linearity of expectation.
Okay.
Okay, and uh, okay, good. And oh yeah, Goel, the chances that this monkey may write an epic is non-zero. Okay, is non-zero because, for example, if you can take any epic like say writing something like Mahabharat, or let's say Iliad by Homer or something like that. I mean, these are huge poems, no? And how many letters do they have? I think something like one, at least maybe at least a billion or a trillion, whatever. So let's say even a trillion, 10 to the power 11 or 12. Yeah, 10 to the power 12. Let's say it has a trillion letters. Notice that this 1 by 26 power 5 remains the same. Of course, this 26 may change because there could be, say, capital letters and small letters and so on. But it remains constant. But this keeps growing. Okay, this keeps growing, and this 5 turns into 10 power 12. Of course, this guy will turn into 10 power 12, and you make this guy keep growing and growing and growing, and the expected number of times that it will write the Mahabharata or the Iliad or Odyssey or whatever, some epic, is very high. So this is what is called
Even
the
the I think even the
infinite.
four changes, the
Uh,
four when it comes into the when we consider the Mahabharata,
yeah.
10 to the power of 9 minus the 4 will be replaced with the number of letters of this
Yes,
Mahabharata.
yes, yes. That's a good point. Yes, this will be replaced by again minus 10 to the power 12, the number of letters in the, yeah, and therefore you should increase this also to make it non-zero. So the bigger so yes, good point, good point. So this is a concept called the infinite monkey theorem. Okay, it says that if you have an infinite sequence of numbers or letters, let's say, if you have an infinite sequence of letters which occur uniformly at random, then you will definitely see um, any sequence you can think of, your name or your this epic or any poem or any C program or whatever in that sequence, you will definitely see it. Not only will you see it, the expectation is infinity, which means it's even stronger. You will see it infinitely often. It'll keep repeating. So this is a very mind blowing analysis actually. Okay, so this you can look it up. It's a very interesting concept. But why did I introduce? Not to introduce the infinite monkey theorem, but I want to make us practice this linearity of expectation and indicator random variables. Okay, we'll do more questions here. Yeah,
One
sure.
quick question.
Yeah,
See, when we consider the infinity, right?
yeah,
Infinite number of times the monkey is going to hit that.
yeah.
So how we write this statement? Expectation of x is equal to. We can't say 10 to the power of 9 or 10 to the power of. It should be 10 to the power of infinity.
Yes, that's what. So we'll use limits, right? So we'll use limits to represent that. So if expectation of x is equal to a limit n tending to infinity and then 10 to the power n minus 4 times 1 by 26 power 5. This is the expected number of times it occurs, and clearly this value is itself very close to infinity. This itself tends to infinity, so it means that the expected number of times your chosen word appears is infinite number of times. It's very large. Okay, good. So yeah, I hope all is clear. I think there was one more chat. Ankita said arg well. Oh, it's 2.111882 for n equals 10 to the power 6. Oh, okay. So it's 2.1882. Okay, that is. But Ankita, you're taking 1 by 26 to the power 5 only, no? Oh, okay, that may happen. That's right. That's right. It could happen. Yeah, it could happen. So let me correct it then. So this should be 2.1882. So it already means that, okay, 1 million is enough to give a non-zero expectation. Good. Okay, thanks. Okay, so let's quickly look at this problem. Okay, okay, 10 to the power 4 from 1 to n minus 3. By using the same method from above, 10 to the power 4 from 1 to n minus 3. Oh, okay, okay, okay. Oh, then you mean it's 2.182. Okay. If it is 10 power 4 many strings and from 1 to n minus 3. So 3 lettered alphabet. Okay, okay. Okay, okay. Great. Thanks. Okay. Sure. Okay, so here's another question. Okay, which says there's a set 1 to n. Okay, each element in a set 1 to n is included independently in a random subset with probability half. Okay, let x be the number of adjacent pairs I comma I plus 1 such that both I and I plus 1 appear in the chosen subset. Compute E of x. So what you are saying is there is a set, okay, 1, 2 and so on n. Now what you do is choose a random subset R, okay, such that um, S, okay, no, not S, let me write it as an element. An element A in S is placed in R with probability half. Okay. Now, let X be the number of adjacent pairs I comma I plus 1, okay, such that, okay, both I they are adjacent, both I they are put in the same set. I and J are placed into that subset. Okay, both I and I plus 1 are put into that subset. What they are saying is compute X, ah, compute E of X, expectation of X. So what does expectation of X represent? Expectation of X represents the expected number of adjacent pairs inside this subset that you create, subset of numbers that you create. Okay, let me show you the question once. Okay, okay, okay. So we've already seen the so this is what we need to compute. Okay, so see, you've already seen one demonstration of linearity of expectation. So here also I want you guys to use linearity of expectation, and I want you guys to use um, indicator random variables. Okay, like before, we broke up whatever we needed to compute e of x. Okay, we broke up x into smaller random variables, which were indicator random variables. I want you guys to try that once. So x needs to be broken into several random variables. X needs to be broken into x2 plus and so on. X m, let's say, and each of these are you. I need you to make it indicator random variables. Can you try?
So here we can think of like say xm. Xm is the random variable corresponding to the subset of the size n.
Subset of
So
size.
because subset of the size n, because here if the size of the set is n, then 2 raised to the power n different subsets are possible.
Yes. Okay.
And then say the size of the subset is n, then within this size m or p, say p is the size of the subset, and then in this subset how many times can I find a pair? So if there are p number of the elements, then what are the chances of getting pairs?
Okay. Okay. But don't get into chances yet. So you're thinking of computing probability already,
Yeah, because then
right?
if the probability is yes, right.
Yeah, you're thinking of computing probability already. So don't jump into probability yet. That's what I would say. First, try to think of the indicator random variables. This breakup.
Yes.
I want see X is the total number of adjacent pairs in this random subset, right? Total number of pairs in the random subset. I want to break up this count into several smaller counts where each of these are indicator random variables. So indicator random variables means either 1 or 0. So is there a straightforward way to do this? So think of the previous problem. We said the x represented the total number of times proof appears. Okay, and xi was the event. It said 1. Okay, xi was the indicator variable which said 1 when proof appears at position 1. Okay, remember that. Now here x is the number of adjacent pairs, and which means I and I plus 1. For example, okay, I'll give you an example. Example is like s is 1 2 3 4 5 till 10, and r is 1 2 5 7 8, 10. Out here, 1, 2, and 5, 7, they are adjacent pairs. Okay, just in case you got confused. Okay, so the count is 2. Okay. Yes, Kishore.
Starting at the, like say the x2 could be the subset starting at the element 2 and then beyond.
Okay, okay. Now you're thinking in the correct direction. Yes. Kishore?
See, E of x, what I am able to calculate is n into 1 by 2 power of 2.
Power of 2. N into 1 by power of 2.
Because n is a set multiplied with the probability, and again when we consider the linearity of expectation, so the I and I plus 1 are the two such pairs. It has to be taken into consideration. So to the probability, what we are trying to add is the count 2.
Okay. Wait, let's see.
Sorry,
Let's see.
n minus something is there. I'm not sure, but n into 1 by 2 to the power of 2.
Okay. Let's see. Okay, we'll check. Okay. So here's the Sohan.
Sir, let's take a set A is equals to only 3 elements 1, 2, 3. So total number of subset possible is 2 to the power 3, 8.
Yes.
And let's take X equals to subsets, and X equals to then possible is 5, 1, 2, 3,
Yeah.
1.
Okay, go on.
Yes,
Yeah,
3,
then, yeah.
1, 2, 1, 3 like that.
Yeah.
Up to 1, 2, 3. In this case, the adjacent values are possible here, like 1, 2, 2, 3,
Yeah.
and 1, 2, 3.
1, 2, 2, 3, and 1, 2, 3. That's right. And
So
yeah.
So in that case, for only 3 distinguishable elements, the total expected value of x should be 3.
Yes.
So in that way, can we find a pattern for like we just extend, insert one more element, and we could find the pattern that how is the expected value of x is increasing. It will take time, and obviously
But that's right. It is an empirical way to do it. There could be other ways to do it. This could be. I mean, you may see a pattern here, and then make a proposition, and then you may try proving it. Okay.
Okay.
But in this case, I want to develop the thoughts to make use of indicator random variables. Okay. So that's why I was telling you guys to not jump into calculating the probability. I know you're trying to calculate the expectations only. Okay. But I want you to exactly think of this point. How to break up X into indicator random variables. Okay. X is the count of adjacent pairs. In the total number of adjacent pairs in X. So Shovan, can you think of what can be X1, X2, and so on till Xn? That's what I'm saying. Okay. Can you try that?
Yes.
See, when we trying to fetch this pairs, right?
Yeah.
So pairs, how many pairs with respect to the set what we have given 1 to n?
1 to n.
The number of pair variables we can make is n plus 1.
That's right. Is it n plus 1 or is it
n plus 1 plus n minus 2 plus n minus 3 and so on till plus 1. These many pairs would be there.
That's a total number of pairs. I think Kishore means adjacent pairs. No?
Yeah, adjacent pairs.
Adjacent pairs is n
plus 1.
N minus 1. That's what I think.
No. See, we go forward way, that is n terms, and then at the last, right, n and the first term will add to the adjacent pair.
But see, what I mean is like 1, 2, 3, 4. The number of adjacent pairs are 1, 2, 2, 3, 3, 4. That's all, no? 1, 2, 2, 3.
Can we consider 4, 1 as well?
No. So 4, 1 won't be considered adjacent, no?
So in that case, I think it's n minus 1.
Yeah, n minus 1. It should be of the form I plus 1. Okay, not I plus 1 mod m.
So I just considered the last term and first term as well. So
Yeah.
probably that is not allowed. So it's n minus 1.
Yeah.
So, and when we are saying indicator variables, what exactly you mean that with that?
Indicator means I want a random variable that is either 1 or 0. 1 indicates some event and 0 indicates all other events. Like earlier we were saying xi equals, okay. See, xi is 1 if proof appears at position I and 0 other, something like this. Yeah, go ahead.
So in this case, yeah, go ahead.
So can I consider this XP?
So for the interest of time, let's take this as the final question for this question.
So
Okay.
XP as the this is indicator random variable, and its value would be equals to 1.
Okay, good.
If we find a pair of the form I comma I plus 1 in a random subset of the size P.
Okay. It's very close, very close. So let me call it x of I. Okay.
X of I would be its value would be equals to 1 if I can find a pair of the form I comma I plus 1 in a random subset of the size I. The size I.
Yes. Okay. Yeah, this is very close, but let me make a slight correction first. So random variables are already random. So you don't need to say in a random subset and so on.
Yes. I mean subset, in a subset of the size I.
So yes. So random. So yeah, it's in a subset of it.
Yes. So, and this entire summation would be carried out over 2 raised to the power n. These many subsets are possible. However, some of the subsets won't be relevant. I mean, which are having size less than 2 and etc.
Yes, this is correct. Subset. Okay, so this R is that subset. Okay, and this is exactly correct. I'll tell you why this is correct. Because yeah, Kishore, just you were saying something.
Yeah, I would say the same thing. The adjacent pairs belongs to R, then it is 1, and else it would be 0.
Yes. Okay, good. Why is this the case? It's the same thing as before. You notice that x equals x1 plus x2 plus and so on till xn minus 1. Notice this. Okay. Why? Because x1 means 1 and 2 belongs to R. Not like this. 1 and 2 belongs to R. And x2 means 2 and 3 belong to R. And so on. If it was 1, by the way, if x1 is equal to, so this says, okay, I'll put a question mark, okay, because it says 1 if yes, 0 otherwise. But if this guy was 1 and this guy was 1 and this guy is 1, it means there are 3 adjacent pairs. Sum them up, 1 plus 1 plus 1, you get 3, which is x, which is supposed to represent the number of adjacent pairs. So I hope this is clear. Okay, this is the indicator random variable that we need here. Now, like before, we want to calculate the probability. What is the probability that xi equals 1? Which is the probability that I comma I plus 1 is chosen. Into R. What is the probability? So what is the
of 1 by 2?
Yes, because include independently with the probability of 1 by 2. So 1 by 2 is the probability with which you'll choose I times 1 by 2 is the probability you'll choose I plus 1. Okay. So you get 1 by 4. Okay. So it's the probability for each xi. Now let's use the linearity of expectations. You want to compute E of x, which is nothing but E of x I plus x1 plus x2 plus x3 plus and so on till x n minus 1. Why n minus 1? Because I plus 1. So the last I plus 1 is not counted. Okay. Yeah, Goel, tell me.
So, I mean, I'm not convinced with this probability calculation that this is 1 by 4, because after it 2 can be, say, the element 2 can be selected in 1 by 2, and its probability is 1 by 2.
Yes.
But then the second element has to be 3 only. So this is no longer, this is no longer remains uniform. There is a condition that the first value has to be a 2.
There is a condition that the first value has to be 2.
I mean, because in this case, even if it is say 2 comma 5, 2 comma say 5 also, then the probability would be 1 by 4.
I mean,
So
see, I'll write it like this. This is equal to the probability that I is chosen and I plus 1 is chosen. This is correct, no?
yes.
And remember that these are independent events because they are included independently and randomly. So choosing I will not influence choosing I plus 1 and vice versa. And so independent events are equal to the product of their probabilities. Right? So this is equal to, this is equal to multiplying these two. Right? Which is half
Yes,
times half. Okay. Are you convinced now?
fine. You're fine. Thanks. Yeah.
Okay, good. So this is what you have now. Using linearity of expectation, you've broken it down. Now, what did we see before? We learned before that in case of indicator random variables, or in case equivalently Bernoulli trials, rather, yeah, indicator random variables. Or is it true for any Bernoulli trial? Okay, I think currently it's not relevant. We are talking about indicator only. Expectation is equal to probability. Okay, for indicator random variables. So, which is nothing but probability of x1 equals 1 plus expectation of x2 equals 1 plus and so on. Expectation of x1 minus 1 equals 1. What did we compute this as? Here we've computed it as 1 by 4 for every I in 1 to n minus 1, right? So we get 1 by 4 plus 1 by 4 plus and so on. 1 by 4 how many times? N minus 1 times, which is n minus 1 divided by 4. So if you create a random subset, okay, choosing with half probability whether to choose or not, okay, you are sort of tossing coins, okay, and choosing, let's say choosing the first toss a coin. If it's head, choose the first element. Toss a coin. If it's tails, don't choose the second element, and so on. Even though you do that, escaping adjacent elements, okay, avoiding adjacent elements is very unlikely. It is n minus 1 by 4. So 25% of the numbers chosen will be adjacent. There will be 25% of the pairs chosen will be adjacent rather. Okay. So this is almost equal to 25%. Yeah, Kishore.
So in this case, did we consider the linearity of expectation?
Did we consider? Yes, of course. Where did we use it? We used it here, getting from here to here. Because we could not have got from first line to second line without linearity of expectation. Linearity of expectation says that E of x plus E of y, E of x plus y is equal to E of x plus E of y. No? So this is what we are
But then
using.
why? But then why did you add this entire thing n-1 times?
Sorry. This should be probability I've written. So here we are doing, no?
This is the probability of what? Yeah, probability of this thing. But then what this? Oh, so what this probability of say x3 is equal to 1 here is?
Probability of x3 equals 1 is also 1 by 4. That's what we proved here. For no matter what I between 1 and n minus 1, probability that xi is 1 is nothing but what we have defined xi as, right? Which is I comma I plus 1 is chosen.
I comma I plus 1 is an element. How did we define xi? Because I remember that we defined xi like
Here,
if there exists an adjacent pair in a subset of the size I.
yes. If I comma I plus 1 is chosen into R, then 1, 0 otherwise. We don't need to deal with sizes.
So do we need not to consider the subsets here? So it's just a matter of literal purpose we are using subsets here because don't need to, while calculating the expectations or probabilities, do we need to consider the subsets as well?
No, that's the way we've defined the random variables completely avoids calculating the sizes of the subsets. That's the nice thing.
Okay.
Because if you deal with sizes, it'll become a bit messy because
No, I mean to
because
say the question doesn't expect us to calculate that part, right?
it does not expect. Yeah. The question does not.
Okay.
But then quite possible that this I comma I plus 1 pairs may be appearing many a times in a
Yeah,
subset.
that's what we get here. Oh, okay. By the way, once you put it, it's a set, not a multi-set. So if you take an element, put it there, it's already taken. You can take the same element multiple times and put it. It's not a multi-set. The duplicates are removed. You get it? No?
Probably I'm missing something, but I'm unable to understand this thing. So how many subsets are possible? 2 raised to the power n subsets are possible,
Yes.
right? And we have to find the count of adjacent pairs in these subsets.
Yes. Right.
And how did we formulate the random variable? So this can this be a simple random variable like its value is equal to 1 if I comma I plus 1 is an element of R. There could be many I comma I plus 1s which are the elements of R and still the value is 1 only. This is not justifiable that since we have to find the count of
Yes.
the adjacent pairs.
Yes. Right.
So that point is not clear actually.
Is it still not clear?
Not clear. Yeah, it's not clear. Probably I'm missing something in the solution or I did not pay enough attention to, but it's not that clear. So I mean, but this, like say, I viewed because the first thing is that the size of the subset somehow should be taken into consideration. Without size, I mean, how can I simply write it as an indicator random variable that its value is 0 or 1?
No.
So what is the meaning of x5 then? What is the meaning of x5?
X5 means element 5 and element 6 are chosen. You don't need to worry about the sizes because the probabilities will take care of it for you.
Oh, now I understood. Yeah.
Okay.
So I was under some illusion because of this size of the thing, but then yes, now it's clear to me. Yeah, I understood. Yeah.
Yeah, Kishore.
Thanks.
So is this X itself is nothing but a number of subsets, right? Or
X is not the number of subsets. X is the you create a subset randomly by picking elements from.
and I mean the random variable. I mean the random variable.
Yes, X is the number of adjacent pairs.
Oh, X is the adjacent pairs.
Yes, in R.
Each element of the set 1 to n is included independently and random subset with probability 1 by 2. Let x be the number of adjacent pairs such that both I and I plus 1 appear in the chosen subset.
Yes.
Okay, okay, okay,
Okay.
okay. So exactly, it's not like we have given 10 elements and then we are choosing only 5 elements from that, and that is a subset.
That you've already chosen the subset.
So for that itself, we are trying to find the probability and the expectation for that subset.
Yes, yes, yes. That's right.
Okay, okay, got it.
Okay. Yeah, I've given this example here. So for example, R is 1, 2, 5, 7, 8, 10. This is chosen randomly. And then 1, 2, and 5, 7 are two adjacent pairs. Okay. Yeah, good. Okay, I hope that's clear. So we have 20 minutes. Okay, let's quickly try this question. Okay. Um, okay, so it's about graphs. Okay. I hope since we are doing a computer science course, I hope everyone is familiar with graphs. Okay, basic concepts of graphs. Just let me know if not. Okay. Consider a random graph on n vertices. Okay. What do you mean by random graph? It means the graph is randomly constructed. Okay. What do you mean by randomly constructed? It means that in that graph on n vertices, every edge occurs with a probability half. Every possible edge is included independently with the probability half. So let's say this is 1, 2, 3, 4. Okay. So it's like you randomly choose an edge between 1 and 2. So by the way, these are directed. Uh, for our purpose, do we need it to be directed? Yeah. Okay. Let's for now assume that it's directed. Okay. Otherwise, the calculation will become really complicated. Yeah. So directed, and there's an edge between 1 and 2 with probability half, and there's an edge between 2 and 4 with probability half. But this is how you can create a random graph. Okay, one way to think about it is like if you want to choose, you want to decide where to put an edge between 1 and 2, you just toss a coin. If it lands on heads, put an edge. If you want to decide whether there is an edge between 2 and 3, you toss a coin. It landed on tails, you don't put an edge. Okay. So and this is by the way a very useful concept in computer science. Okay, random graphs. Okay, and let x denote the number of edges in the graph. Okay. Now the question itself is guiding you here. Okay. Define indicator variables for each possible edge in the graph. Okay. Define indicator variables for each possible edge in the graph. So here is how I can define indicator variables. Xij. Yes, Goel. Right, right. That's right. Yeah. Can you help complete this? Goel.
So its value would be 1 if there exists an edge from the vertex I to the vertex j.
Yes.
Otherwise, its value would be 0.
Right, good. And otherwise, it's 0. Good. So now can you tell how do you compute E of x? So, and by the way, they are saying x is the number of edges, the random variable x is the number of edges in the graph. Okay. Now what I need to compute is expectation of x. How do I do that? Using linearity of expectation.
Yes, yes, yes. So that would be the x11 plus x12,
Yes.
and then so on, and then so we can write this. We can use a shorthand notation to write this summation of xij's,
Yes.
and double summation, and then I varies from 1 to n, and j varies from 1 to n.
Yes. So summation I and j
Yes,
from 1 to n.
and
Okay.
xij.
And xij. Good. Right? I hope this is clear by looking at the previous two questions. Xij tells whether there is an edge or not. X tells how many number of edges are there in the graph. So when I sum them up, when I sum Xij up, the ones contributed to this sum are exactly by those Xij's which are equal to 1, which represent whether that edge is there or not. So which means X is nothing but the number of edges in the graph. I hope that is clear. Is that clear? Chauvin, Kishore, Ankita. IJ represents nodes. Yes, sorry. So IJ. Thank you. Yes. IJ represents nodes in the graph. So the nodes are okay. Vertices of G is 1, 2, and so on till end. Yeah, thank you for clarifying. Ankita is asking, so it cannot be the same. If it becomes the same, it will represent a self loop. Is that harming this question? That's what I'm thinking about. Yeah. Is X11 edge is possible? It means that there is a self loop. Ankita. Let's see if I encounter a problem. But thanks for asking this clarification. If I encounter a problem, I'll just change the question. Okay. For now, I've just assumed that it's directed. If it's undirected, I need to choose a set, and anything else will change. Then xji will be equal to xij. That's one thing that will happen. Oh, but yeah, great. No, we don't need to do that. It need not be directed also. Okay, let's see. Okay, for now, yeah, there could be self loops also. We'll just assume. Okay, great. So yes, so everything is good, right? Uh, yeah, Kishore, Sovan, convinced so far. Okay, good. Shovan, okay. Who else is there? Uh, yeah, Rajnish, Bhumika. I hope everything's fine. Okay, just let me know. So far we are good. Now, okay, use linearity of expectations. Anywhere you see random variables getting split into sums, expectation of x is now I'll directly do it. Okay, it's the sum of expectations of ij. Okay, and now what is this? We know that in random variables the um, in random variables sorry, not random variables, in indicator random variables, expectation equals probability. Okay, so which is summation I comma j in n uh, probability that xij equals 1, which is nothing but the probability whether the edge is present or not. Can you tell me what this is equal to?
1 by n.
No, not 1 by n. What does the question say?
It's 1/2 already given.
1 by 2. Okay, we are tossing coins and deciding.
Okay.
Okay, so summation I comma j in n half. Okay, so I comma j half. But half you are doing how many times? I comma j is in n times, which is n square many times.
And
Yeah, Rajnish.
n square by 2.
N square by 2. That's right. So n square times 1 by 2, which is n square by 2. So what it means is usually when you create random graphs, okay, the number of edges you should expect it to be pretty large because already total number of edges you can create in a directed fashion is n square. Okay, and half of n square, it's still a pretty dense graph. Okay, so this is used like in adversarial arguments or in like networks, things like this, where you expect what is the kind of network you expect. You expect a rather dense kind of network. So usually if you see any kind of graphs in practical life, usually they are dense graphs. They are hardly sparse graphs. Okay, because you expect them to be dense, like 50% uh, edges is at least there. Okay, now comes the interesting part. I want you guys to try this. Can you similarly compute the expected number of triangles in the graph? Okay, let's see. compute. So let me write y, okay, or let me write t. T is the number of triangles in the graph. Okay, and what is a triangle? Triangle is something like this. Okay, so let's say
For triangle, will it be n cube by 2?
okay, Goel is saying 1 by 8, but we want expectation on t. Yeah, yeah. Sorry, who said Rajnish? What you said? You are breaking up a bit, so that's
I said that for triangle,
triangle
will it be n cube by 2? Because for triangle, will it be n cube by 2? Because
because
now we are taking only two nodes, I and j. But for forming a triangle, we need one more node, I, j, and k.
right.
So then it will be n cube by 2.
Okay. That's a good thought.
Since the probability is 1 by 2 for every vertex.
But I want to ask you, Rajnish. So sorry, this is not expectation. Expectation
Yes.
t. Okay. So will the previous still hold? You said 1 by 2, no? But that's when we are doing x1 plus x2 plus so on, right? But is it still holding? That's not the case. No, this will count the number of
Yes,
edges.
sir.
This will count the number of edges. So I want to count the number of triangles.
Okay.
So I want to come up with a linearity t1 plus t2, t1 plus t2 plus and so on till tm, let's say. Okay. Now, what should be the indicator random variables? You're thinking in the right direction. You've got it halfway. You've got it halfway. That I need to go across k also. Yeah, Goel is saying ijk. Yes, Goel. But what are these indicator random variables now? That time indicator random variables was this. Where is it? Xij equals 1 if the edge ij exists, right?
So that would be like similar to the previous problem, I comma I plus 1 comma I plus 2. That kind of the thing, a triple
Okay.
should appear, and that will form a triangle.
Okay, so let's say is summation of I j k, right? Oh, okay, that you said t uh, oh, okay, that's what you mean. So you mean t I j k is 1, sorry, t I j k is 1 0 if I j is an edge, something like that.
Yes, ij is an edge, and this, I mean, there should be a relation between ij and then k, so that this forms a triangle, and that would be when one is connecting to two, two is connecting to three, and three is connecting to one.
Right.
So for that thing to happen, I mean, all the three conditions should met simultaneously.
Yes.
That I comma j is an element of E, and j comma k is an element of E,
Yes.
and then k comma I also an element of E.
Good. Yeah. J comma k is an element of E, and k comma I is also an element of E.
Yes.
Otherwise, good. And can you tell me the probability of T I J K happening?
That would be 1 by 8. I mean, that is what I wrote earlier. That
Yes.
because of this uniform thing. Yeah.
Yes. Good. So probability is 1 by 8.
Okay,
now
so
you have
due to
yes
three nodes I, j, and k, we have n cube by 8.
n
is
cube by
the
8. Good. Yes.
expected.
Yes.
Yes.
Right. Okay. So expectation of T will be equal to n cube by 8. Good. Now, you can also alternatively do, instead of introducing T1, T2, and so on, you can alternatively do, okay, alternatively, T is equal to, or you can also see, so alternatively, yeah, T is equal to summation I equals 1 to, so sorry, ijk, summation ijk Okay, xij times xjk times xki. Recall that xij represents whether there is an edge or not. Okay, when will this sum contribute to when will a term in this contribute to a 1? When this is 1 and this is 1 and this is 1, which means there is an edge from I to j, there is an edge from j to k, there is an edge from k to I. Okay, this is an alternate way to do it. So which is equal to summation ijk. So then you have the expectation of t equals, sum across the probabilities, probability of xij, probability of xjk, probability of xki. This is an alternate way to do it, ijk, and this is half times half times half, which is, so, and this is going over n cube, so which is equal to n cube by 8. Okay, this is another way to do it. What I'm trying to say is, because they are indicator random variables, multiplying them represents two events happening at the same time. Okay, and therefore you can do some sort of algebra over random variables also. That's the point that I was trying to make. It's not only about adding random variables, multiplying random variables represents two events happening at the same time. Indicator random variables, mind you. Okay, and multiplying three indicator random variables indicates three events happening at the same time. Okay, ij, jk, and ki edges being there. So this is an alternate way to do it. Yeah, okay.
And this is Ardos Rennie network, I guess. If the connection probability in general is given as p, not
Yeah.
specific to half, yeah. This
Oh,
is
this is
ER network. Ardos Rennie network.
yeah. I think this is Erdos what?
Rennie, RENYI. Ardos
N
Rennie, REN for
N.
yeah, YI. Ardos Rennie.
Oh, Erdos. Okay, thank you.
Yeah.
Yeah,
Yeah.
I thought this was due to Erdos, but I didn't know that it's established as Erdos. Yeah, thanks. And this theorem sort of says that triangles are very common in graphs. Okay, you should expect to see a lot of triangles in the graphs.
Yes, because a triangle shows the friendship or the possibility of having a friendship. Like if one is connected to J is connected to K, then there are higher chances that K could be connected to I, and this could be one of the, I mean, measure of recommending friendship. That
Yeah.
okay, this person may be connected to you. Yeah.
Yes. Good. Yeah. Yeah, that's a good connection to social sciences.
So the other way to consider the triangle with respect to the edges are, see, if ij are both the edges, so the adjacent edge for the ij can be considered as a triangle, right? If there is an adjacent edge which for the ij, then that three edges can form a triangle. Is that the right way of thought process?
Let's see. So what did you say? Okay. So I have ij here.
Right.
Okay.
So I have another edge
Okay.
which is adjacent to these two edges.
Adjacent to edges. But what do you mean by adjacent?
I and j are edges. As per our assumption, I and j are edges.
No, I and j are vertices.
What is this? Okay.
So xij represents whether there is an edge between I and j.
Okay.
Okay. So that's why we said xij times xjk times xki, which means there is an edge from I to j, times, which means from j to k, and times xki. Okay. So when there are edges, these represent ones, and this entire term becomes one only when all three of them are ones. Means these edges are the same. Okay. Yeah. So and but this is yeah. So but this is interesting because like if you have a what how many edges do you need to put in this graph in order to make a triangle? No, you can put 1 to 2, 2 to 3, and then 3 to 4. You can avoid it by adding n edges, and then finally you'll add an n plus 1th edge, and then it will form a triangle, definitely form a triangle, right? So you need at least n edges to do that. But so you expect the number of triangles should be a bit difficult to get. Like even one triangle, you need to add at least n edges to guarantee a triangle being there. But using probability, we say that, oh, if you randomly come up with a graph, the number of triangles, not only does it exist, but it's huge. The number is huge, n cube by 8. Okay, and as n grows closer to infinity, it's the 8 does not even matter, right? Okay, good. So okay, I had prepared like 8 questions in total, but we've already reached 8 o'clock. So I could only do 3 questions, but it's okay as long as all the concepts were clear. Okay, what I really wanted to emphasize on was linearity of expectations and use of indicator random variables. So I'll be uploading this document in the drive also. Okay, you'll be getting an email. Okay, which will have the link to the drive also. So there are other questions here. Please try these questions. Okay, there are some, and I'll just write this. Okay, this is so please try these questions. Okay. So this is called like we have the law of total probability. We have law of total expectation, which says that um, let's say A1, A2, A3 uniformly partition, not uniformly, partition, they are disjoint events. Okay. And they partition the space. Okay. Can you share all questions in the form of PDF? Yes, that's what, Ankita. I share it on the drive, Google Drive, and the drive, the link they give it to you. No, they should be giving you a link after every recording session. But let me just um, share it to you. Okay. Um, copy link. Okay, I've put this Google sheet here. You'll get it in the email also. So there is a drive link there. I usually upload it there. Okay, and please try these questions. If you have any issues, just let me know in the next session. Okay, and I was just saying that this expectation of x given a can be written as expectation of x given a1 probability of a1. Remember the total law of total probability. It's similar to that. Expectation of x given a m probability of a m. Okay, and the same principle is used in this question also. And okay, this is a more difficult question, but please try it. And this is a very difficult question, but you can still try it. It's a very interesting application, although I feel like you'll see it later in the course. Okay. Thank you very much. Need to log off as I have to catch up with some other work. Yes. Okay. No problem. Okay. That's all. Okay. So if you don't have any more questions, then feel free to leave. Yeah. Thank you. Well.
Thank you so much. Bye.
Yeah. Thank you. Bye. Good night.
Good night.
Yeah. Okay. Thank you, Kita. Thank you, Shovan.
Right. Thank you,
Thank
sir,
you,
for
sir.
this insightful session.
Yeah. Thank you, Rajnish. Thank you for attending. Okay, thank you, Bhumika. I am ending the meeting.